This is the video for section 11.3 on the integral test. And the idea for the integral test is very similar to one that we had for sequences, except for this is a test for testing convergence or divergence of series. And the test works like this. So the basic idea is that we want to have a series where the terms of the series are given by a nice function. So we have to start with a function f of x that's continuous, positive, and it should be decreasing on some infinite interval. So let's say that it's true on the interval from k to infinity. And we're going to assume that the terms of our sequence are given by this nice continuous decreasing function. And we have two situations. One is if the integral from k to infinity of that function converges, then we get to conclude that the series also converges. And part two, this is a perfect test. It says that if that integral diverges, then the series also diverges. So, unlike the test for divergence, which only allows us in some cases to conclude that a series diverges, it never allows us to conclude that a series converges, this integral test is perfect, that it allows us to actually conclude either convergence or divergence, assuming that we can check that that integral actually converges or diverges. So, for example, we can consider the harmonic series that we talked about in section 11.2. So this is the series sum n equals 1 to infinity of 1 over n, and we know from section 11.2 that this diverges. But I want to give another explanation for why it diverges, and one that's a little bit less technical. And the point is that this function, f of x, 1 over x, is continuous, positive, and decreasing on the interval from 1 to infinity. And that's because the graph of that function has this shape. And we know that the integral from 1 to infinity of 1 over x dx, so we compute that as the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. When you evaluate that integral, we have a natural log function. The natural log of 1 is 0. So we end up with the limit as t goes to infinity of ln of t when you work out that integral. And of course, as t goes to infinity, ln of t also goes to infinity. So that says that this integral diverges because I have an infinite limit. And so the conclusion by the integral test that this harmonic series also diverges. More generally, you can use the integral test in order to evaluate any so-called p-series. So I'll list this as a fact. It's that if I look at any series of the form summation n equals 1 to infinity of 1 over n to the p, then this converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. And you can verify this by using the integral test, just like we did with the harmonic series in the previous example. And this is done in example number 2. I would actually, this type of series is going to be incredibly useful for us in the future, so I would memorize this fact. So add this to your list of series like the geometric series that are important for us. And speaking of the geometric series, here's a warning, is that the p-series, which is the sum n equals 1 to infinity of 1 over n to the p, is different from the geometric series, something of the form summation n equals 1 to infinity of 1 over r to the n. Right? That is a geometric series. The point is that here n is in the base of the exponential expression, and over here n is the exponent in the exponential expression. And that makes these series behave very differently from one another. Essentially, the left-hand one is a rational function and the right-hand one is an exponential function, and those have very different behavior from one another. So you want to make sure when you are looking at series to make sure, if I'm saying I have a p-series, do I really have a p-series? So a couple of examples here. So for instance, if we want to look at the summation n equals 1 to infinity of 1 over n squared, this is a p-series with p equals 2, which is greater than 1, so I know that this series converges. On the other hand, if I have the summation n equals 1 to infinity of 1 over the square root of n, so that's the same as n equals 1 to infinity of 1 over n to the 1/2. That's a p-series with p equals 1/2, which is less than 1, and so I know that this one diverges. Okay? So this gives us a very fast way of testing whether or not series are convergent or divergent as long as they fit into the particular form. Okay? And an example like this you can see in the text. You can look at example number 3 for a nice p-series example, and you can look at example number 1 for another example where the integral test is used explicitly. Now, one thing to note about the integral test and the p-series test, these tests only tell us whether or not a series converges or diverges. They don't actually give us any information at this point about the value of the series. And for example, it's incredibly hard to actually compute the exact values of the p-series that do converge. So that means that the best thing that you can hope for frequently is to be able to get a good approximation for the value of a series. And that's what we'll talk about next. So here we're going to talk about estimations, or if you like, approximations of the series n equals, let's write it this way, I want to use the index k here, the a sub k, where again a sub k is given by some nice function f of k, assuming again that f of x is positive, continuous, and decreasing on some interval from n to infinity. Now, if we call this full sum up here S, and we have the nth partial sum Sn, so that's the sum k equals 1 to n of a sub k. Then the first fact we're going to have is that the difference between S and the nth partial sum is less than or equal to the integral from n to infinity f of x dx, and it's greater than or equal to the integral from n plus 1 to infinity of f of x dx. And so what this tells us is this tells us how bad the error is. So this is the error, which we generally denote by r sub n. R here is for remainder, gotten from approximating S by some nth partial sum. Okay, so what's the point? The point is that you may have a series where you add up a bunch of terms, and we'll see this in just a second, and you want to, say, add up 5 terms and say that's a pretty good approximation for my series, but we want to know how good of an approximation that really is. Okay, so let's look at that example on the next page. So for example, if I want to look at the summation k equals 1 to infinity of 1 over k to the 4, that's going to be approximately, so this would, in the notation from the previous page, this would be my S, and this is going to be approximately, say, S5. So I'm going to use the number n equals 5 for my approximation. So S5 is just a shorthand for writing the summation k equals 1 to 5 of 1 over k to the 4th. So that's 1 over 1 to the 4 plus 1 over 2 to the 4, and so on. Up to 1 over 5 to the 4th. And if you plug this into your calculator, something like that, you get that this is approximately 1.08035193. And your question is, how good of an approximation is this for the entire series S? And what the previous fact that we had says is that the difference, S minus S sub 5, is less than or equal to the integral from 5 to infinity of 1 over x to the 4 dx. First of all, and let's see where that comes from. So the fact that I have a 5 here is telling me to put a 5 here, and the fact that I have 1 over k to the 4th here, that tells me to use 1 over x to the 4th here. Now, the other side, this difference is greater than or equal to the integral from 6 to infinity of the same function, 1 over x to the 4 dx. And if you write these out, this left-hand integral ends up being 1 over 3 times 6 to the 3, which is approximately 0.0015431, and this right-hand integral is 1 over 3 times 5 cubed. And that shouldn't be obvious to you at all. You need to write out this integral as a limit, compute the antiderivative, plug in the endpoints, and take the limit. You need to do the entire process of evaluating that improper integral in order to get the equality that I have written down here. And this value is, let's see here, 0.0026667. Okay. So that tells us that the error here is somewhere between 0.003 by rounding up and somewhere greater than or equal to 0.001 by rounding down. Okay, so the point is, if you only care about a couple of decimal places, then choosing n equals 5 for this sum is actually giving you a pretty good estimate for the sum. Now, there's another formula that we get coming from the previous one that allows us to get even slightly better estimates as follows. So the formula we had before said that the integral from n plus 1 to infinity f of x dx is less than or equal to s minus sn less than or equal to the integral from n to infinity of f of x dx. And now if I add Sn to all three of those terms, that I end up with Sn plus the integral from n plus 1 to infinity f of x dx less than or equal to s less than or equal to Sn plus the integral from n to infinity f of x dx. And so, for instance, in our example, this tells me that the complete sum that I was trying to compute is somewhere in between the summation k equals 1 to 5 of 1 over k to the fourth plus the integral from 5 to infinity of 1 over x to the fourth dx. And this is greater than or equal to that same partial sum, k equals 1 to 5, 1 over k to the fourth, plus the integral from 6 to infinity of 1 over x to the fourth dx. Now we've already evaluated all the pieces here, so this says that, right, so this left-hand side is approximately 1.08035,193 plus 0.00154321, and that gives us a total approximation from the bottom of 1.081895139. This right-hand bit here, I have that that's approximately the same first bit, 1.08035,193, right? And let's just be clear where those numbers are coming from. Those are coming from the computations that we did on the previous page, plus another computation we did on a previous page, which is 0.0026667. And so this right-hand side is approximately 1.083018596. So if I take this right-hand side and I round it up, and I take the left-hand side and I round it down, then what I find is that 1.081895113 is less than or equal to the sum k equals 1 to infinity 1 over k to the fourth, that's my s, and that sum is less than or equal to 1.083018 6 0. So we've got a pretty reasonable approximation there. A good estimation right, so I have a lower bound for that series and I have an upper bound for that series, and that tells me in some sense that a really good bound would be to split the difference and take the average. In other words, I'm going to take the midpoint of the interval that starts here and ends here. And so this is saying that S is approximately 1/2 times, and let me not rewrite these, the red number plus the blue number, and that ends up being 1.082456865. one thing that's worth noting about this example, let me see, I'm going to put this over on the side here so that we can compare it directly, is that the actual value for this series is somehow pi to the fourth over 90. And this is not in any way obvious. This is actually really, really challenging to prove this fact. But if you plug this into your calculator, you get this number, 1.0823232337, as an approximation, which is pretty close to the approximation that we got down here. Okay? And you see why it's good to take the average between the red number and the blue number that we had as the bounds from above. Okay? Some examples from the book to keep track of. I'll write these on the next page. Yes, I'll write them right here. Is to look at examples 5 through 6 in the textbook. And I think this is a good point to stop. This is the end of the lecture on section 11.3 on the integral test.